perdón, un contrato postdoc GEN, creo que se llama. Eso le asegura volver aquí a la UJI y seguramente en 2, 3, 4 años, pues seguramente conseguirá una plaza de profesor titular. Es decir, es el ejemplo que a mí me gustaría para mucha gente a los cuales les he dirigido la tesis, están esparcidos por el mundo. La universidad, la Comunidad Valenciana en España, se ha gastado mucho dinero en eso, en becas, en contratos, etcétera, etcétera, y sin embargo todo ese conocimiento lo aprovechan otros países que no han invertido prácticamente nada. Eso no es lógico. Lo lógico es que esta gente vuelva. Es decir, yo siempre hago el siguiente símil. Yo no conozco la Universidad Jaume I, yo no conozco a la facultad, al departamento, yo no sé quiénes son. Realmente a los que conozco son los que trabajan ahí, a las personas. Y tener una universidad de futuro, lo que tiene que hacer es recuperar todo el capital humano y además con la inversión que se ha hecho desde Valencia, la universidad y en España para que esta gente no haya otros países y otras universidades o centros de investigación que se aprovechen de esa inversión que prácticamente no les ha costado nada. Vale, pues nada, Carlos, adelante.
Sí, muchísimas gracias, Juan. Ha sido a gusto volver con ese tipo de recibimiento. También muchas gracias por la invitación a todos los organizadores. Un poco voy a dar la charla en inglés. Os quería contar un poquito la trayectoria, porque lo ha mencionado ya Juan. Yo hice la tesis aquí en el grupo de óptica. De hecho, colaboré con muchos de vosotros, con Juan, con Nelson, sobre todo en la parte del profesor San Miguel estaba mencionando, de radiación con láser de femtosegundo, de tungstanato de plata, fosfato de plata también. Y bueno, trabajamos sobre todo en la parte de láser y después pues acabé la tesis, fui a la Universidad de Duisburgo-Essen y después a la Universidad de Wuppertal. Y hoy os voy a enseñar un poquito mi trayectoria de vuelta con la GENT, con el programa GENT, las cosas que también he aprendido en Alemania y que quiero incorporar un poco en España. So, let me change into English. What I want to show you today, basically, it's my basics from the thesis. We were working mostly on the generation of nanoparticles with laser, the generation of nanoparticles in liquid, but also we have done irradiation in air, so to modify the properties of materials, to provide bactericidal properties, to provide other functional properties. And what I have learned mostly in Germany is to use these nanoparticles that we can generate to increase or to provide extra properties to materials that we can produce by additive manufacturing. That is quite a general topic nowadays. It's a lot of different techniques. We are mostly focused on the ones working with light because our expertise is coming from light science, from optics. So, but now that I'm here, I want to also to highlight a bit the group here in Castellón. So we have a lot of different research lines involving mostly the treatment of light for scattering media, for example, to see through scattering media, also computational imaging. And the part that I'm more involved, the part of the group from Professor Gladys Minguez, is the laser material processing and synthesis of nanoparticles. Here, finally, I have this slide that I will show 3 times in this talk. Why 3 times? Because I want to highlight 3 of these topics that I show here. This is the main chain that we try to develop, or we developed in Germany. The idea is to take nanoparticles that here we have a target, a material, we irradiate with the laser, and we generate nanoparticles in the liquid that we want, some colloidal nanoparticles. The idea is not only stopping here, we have a lot of freedom, as I will show now. It's to take these nanoparticles and add them to materials that are already employed in additive manufacturing. In additive manufacturing, we can employ microparticles, we can employ photopolymers or resins, and even bioinks or filaments also, that is the most standard. What we want to do next is, by adding these nanoparticles, we provide extra properties to the material, and then we just print them as they are usually printed, by powder bed fusion, for example, directed energy deposition, or maybe the most standard that are the photopolymerization, this stereolithography, or VPP, and material extrusion, that is the filament printer, the standard filament printer. So, why lasers and nanoparticles? Where we are joining 2 worlds. We are joining the photonics world, we are joining the nanotechnology world. And the advantages of this technique if you are not familiar with it, what we do is basically take our laser, put some target in a very easy way, and what we do is scan the surface. So it's the same as we do when we are processing a material. We are usually interested on the surface, but in this case, we are interested on the material that is coming out. And if you want to see an easy implementation, check the video. So we just place some water, we just place the target inside, we put the laser, and you see how we are generating directly the gold nanoparticles in this case. It's just a gold target, and we have the plasmonic response. So if you want to check more of these videos, you can check this YouTube channel from the University of Wuppertal. Another option with the laser is to take materials that are already microparticles, for example, and then just use the laser to break them, basically. So here, I don't know if it was starting directly, but here we have the same solution. Some are gold nanoparticles, but are in larger size, around 100 nanometers, and we irradiate them with the laser. And what happens after some time? Well, we are just breaking these nanoparticles into smaller sizes, and what we achieve is, you will see it by a change in the color of the solution once the irradiation process is finished. You see that from the starting same color in both cases. Here, we reduce the size, and since the plasmonic properties depend on the size of the nanoparticles, we are returning to nanoparticles of around 20 nanometers, more or less. So it's not only a technique that we can use for the bulk, but also for suspensions of microparticles. And why do we like it? Well, we like to produce a lot of different nanoparticles. We collaborate with a lot of people in different applications, from catalysis to biomedicine, because as you can imagine, we can produce the nanoparticle just in the liquid we want and with the material we want. So we don't have a lot of byproducts in the process. So the purity is quite high. The surface, we have been talking a lot about surface of nanomaterials or materials in general during this session. So we have quite, let's say, surface, ligand-free surface in many cases. And we like these nanoparticles for, as I was saying, catalysis, fluorescence imaging, for example. And today I will focus mostly on the additive manufacturing part. So here I return to my previous slide. I have shown you a bit of the advantages of this laser nanoparticle generation. And now what I want to show you is the main process of how we take them. We put them in one material, in this case, microparticles, and then we do some printing with, for example, powder bed fusion. I will do it first taking silver, putting in microparticles, and for powder bed fusion to generate bactericidal parts, bactericidal materials. And in the second case, I will show some photopolymerization example where we add some nanoparticles to the resin, and then we print some magnetic actuators. Okay, why additive manufacturing? Well, it's a group of techniques that are being developed and have gained a lot of attention in the last decade or 2 decades. The possibilities that these techniques offer is that you have custom fabrication of elements without employing extra materials, because for standard industrial production, we have a lot of very well-developed technologies to print materials. In fact, injection molding is the pretty standard, and we cannot compete from the additive manufacturing in that sense. The problem comes when you want very specific geometries on very specific objects. And for example, you can see some examples here. Some materials are more tricky to print by injection molding, and some materials, even like these shoes, you can see the intrinsic geometry. So inside of this shoe, so this is empty. If you want to do this by injection molding, it's pretty difficult to fabricate a mold that you can just put the material. In that sense, additive manufacturing can directly print all this structure in a single step, let's say, without several processes. And within the many different applications that we can talk about in this field, one that I like a lot, it's the medical application. Why? Because in medical, you have one of the biggest problems in terms of you cannot do always serial production. If you want to do some scaffold, or if you want to do some denture or some different medical elements, each patient will require a different geometry. So you cannot make standard scaffolds, for example, and use for everyone. So each person will have a different situation. In that sense, printing with additive manufacturing can make it very cost-effective and very easy to prepare scaffolds for every specific application. And, well, even going a bit inside this, what you can think is, okay, but you are printing some scaffold, and there are some extra problems that can come from the medical sector. That is, for example, infection and development of bacteria. What we can do is take our nanoparticles, add them to the materials that are employed for the scaffolds, and then try to provide extra bactericidal properties to the printed sample. And how do we do this? Well, I will go through the process step by step. So in this case, we are going to use a micro powder. So these are microparticles of a polymer. It's nylon. It's PA12. So what we basically just do is to take the microparticles, put them together with our colloidal nanoparticles, and then control the pH to achieve that the nanoparticles go to the surface of these microparticles. And you can see from the initial powder, after we add silver, you can see the typical plasmonic coloration of the silver, the yellow color. What we do afterwards is just the regular printing of these materials. So use this laser powder bed fusion that is fusing the material, and then we can print some samples that still keep the nanoparticles on the surface. Here you see an example. So we start our process in our lab with our laser. We irradiate some gold silver target immersed just in water. We generate nanoparticles in the liquid. You see here the colloidal nanoparticles around 10 nanometer size. And they have this distribution, this plasmonic absorbance in the 400 nanometers, more or less. Then what we do is just adding the PA12 micropowder, the nylon microparticles, and then we control a bit the pH, and then we achieve that the nanoparticles go to the surface of this powder. And you see that we are able to transfer the plasmonic response of the initial silver to the powder that we are preparing. Afterwards, we print it with the laser. So we are just spreading the powder, and then with the laser is basically melting the material or sintering the material, and then forming this solid structure that still keeps the same plasmonic response. Why is the plasmonic response interesting? Well, because as we have seen previously, if the size of the nanoparticles change, then we will have a displacement of this peak. So this is telling us that the nanoparticles keep approximately the same size as at the beginning of the process. Here you see some pictures. It's quite nice when we do this with polymers. We have done it also with metals, but the point is when we do SEM, so the silver has a quite high contrast and the polymer much lower. So all these bright spots, you can see that are the silver nanoparticles supported on the surface of these nylon microparticles. Here you see that if we measure the size of the nanoparticles on the surface, it's pretty similar to the initial one, maybe just a small enlargement, but it's common. And what we wanted to do with this was some, well, let's say preliminary in this case, measurements of the bactericidal response of the finally printed material. Because why we want to add silver, right? We are making the material more expensive. We need to have some advantage compared to the base material. Well, the first test that we did was just to take this printed part, put it inside some Petri dish with some water, with some, PBS, some culture media, and then we removed the part. We did the same with the parts without the silver. We took this liquid and, well, we took it with in collaboration with a center in Hanover. They did the bactericidal test. And what they did was trying to grow the different bacteria on this culture media that was having the presence of the parts of the printed parts. So here you have the well, preliminary or the initial test that we did. So here you have the control. So we have the PBS where the bacteria were growing quite well. We have the chlorhexidine where most of the bacteria or all the bacteria, there was no growth there. So there was inhibition of growth. And here we have the two samples of the liquid after we just immersed the base material, the nylon part. And here, what we immersed was the nylon part with the silver, the PA12 part with the silver. And you clearly see the difference. So in the case of the base material, when the bacteria can grow, there is no change compared to the base culture media. In the case of the part where we added the silver nanoparticles, we have an inhibition of the growth. Okay, so are quite, as I say, it's the beginning, let's say, but we have, if we can see it a bit more quantitatively, we see that there is basically no difference between the PA12, the base material, And then we have almost complete inhibition when we use the Pe12 with our silver nanoparticles. I should say that also the silver concentration is pretty low. So it's only 0.1 weight% compared to the base polymer. So in terms of the price, that's also a big advantage, let's say, because you want to keep a balance between the price and the functionality that you are providing. Okay, and finally, the final application that I want to show you, it's a different case. It's using a resin, a photopolymer, adding magnetic nanoparticles, and then doing the printing by photopolymerization, and then seeing if we can print some magnetic actuators. This is a different approach. But basically, I like this one because you see that the approach, basically the general approach is the same. What we change is materials in every case, but we can do it following a similar step. So here, what do? We just take our chamber. We have some iron nickel. We chose this material because it has high magnetization. We just produce iron nickel nanoparticles in acetone, in this case, in an organic liquid. We increased a bit the concentration to limit the amount of acetone that was in contact with the photopolymer. And we just do the mixing of these nanoparticles with the base photopolymer that is used in stereolithography. We take this new material, and the extra thing that we did was modifying the printing setup. So instead of doing, usually this printing technology is based on UV light that is coming from below, and then we have a tank with the photopolymer. And then this UV light is basically solidifying the photopolymer in the area that is interacting. What we did was to add some magnets on the side of the printing tank. Why the magnets? Because this is doing some orientation of the nanoparticles. If we have just dispersed magnetic nanoparticles, when we print something, we will have some magnetization, we will have some magnetic properties, but not spatially resolved. So they will be just homogeneous. If we can do an orientation of these nanoparticles, well, here you can see the size distribution of the nanoparticles and their magnetic response. But if we do some orientation of these nanoparticles, what we are achieving is basically this situation. So when we are moving from a situation with a stronger magnetic field to less strong, and also changing the concentration of acetone, we can go from a situation where these black spots are the iron nickel, nano, or here even larger particles. They are more or less homogeneously distributed. When we are increasing this magnetic field, and we are also increasing the amount of acetone, because that's also changing viscosity and the particles can move easier or with more difficulty, we can achieve this, what we call these nanostrands, or that is this linear chains that we are forming that are aligning with the magnetic field. And when we are printing it, this gets fixed in the material because we are solidifying the polymer, and this gets fixed in the process. So let's say that basically during the printing, we are doing like two processes. We are doing the printing, that is the standard, but we are also doing the alignment of the nanoparticles. And these strands are quite interesting because with this, if we control the printing as we want, so we can achieve different actuators. And that's quite interesting for robotics, for example. And the actuators that we tried, and with this I finish, we tried some rotors that is basically to control by an external magnetic field. We can control the rotation of these micro or millimeter scale structures that we were printing, and also some gripper. So we can control the opening and closing of the gripper just by an external magnetic field. That's very interesting, for example, for, as I said, robotics in ambience where you don't have direct access. For example, in microfluidics, you sometimes cannot access directly mechanically to do the rotation. So you want some external magnetic field so that the liquid is flowing. And the gripper the same. In some controlled atmosphere, you don't want to add some extra components inside. And just to finish, these ones, I think I need to activate them. But here you see the videos of the actuation, some with better view of the magnets, I think are seen a bit here on the side. It's quite focused. But here you can see it's not a very strong force. I mean, we did it for a low loading of nanoparticles, so you can play with the force and with the momentum that you can actuate by changing the concentration. We started just with a proof of concept, let's say. And here you can see the gripper, and here you can clearly see how we are doing the movement by basically rotating a magnet. So you can see it here, the magnet rotating and how we can control the opening and closing of this, well, let's say easy actuator that we have. Okay, so with that, just conclusions. I hope I have convinced you that generating nanoparticles by laser is a quite, well, good technique and also quite versatile. You can generate a lot of different materials in different liquids. So in case any of you is interested, we could talk about options here for catalysis, for biomedical applications, for many applications. And from the application point of view from our side, so I hope that I could convince you that we can print magnetic photopolymers. We can generate some magnetic actuators. We can, of course, provide also plasmonic properties to the printed parts. That's also interesting from the optical point of view. And also we can even provide some bactericidal properties to the printed objects. I would like to thank the group in Wuppertal because most of this group was developed here. So I'm really thankful to Bilal Gokce. Without him, I wouldn't be here right now. Of course, also the group here in Castellón, so all the people. And finally, yeah, especially to the GENT program and Generalitat Valenciana, because as Juan was mentioning, so thanks to this kind of programs, I'm able to be back home after only 4 years outside. So I think it was quite lucky. And if you want to get in touch, please get in touch anytime or here. I will be also tomorrow. Thanks a lot.
Vale. ¿Cuestiones? ¿Preguntas?
Gracias por la charla, la verdad es que es increíble lo que haces. Son 2 dudas. Una es, el láser que usas es pulsado, entonces, ¿qué sueles usar, femto o nano? Y si hay un cambio en el tamaño de partícula que obtienes o lo has...
Sí, sí. De hecho, ahí no me he metido en la primera parte, pero ahí puedes jugar muchísimo. Normalmente en Alemania usamos sobre todo pico, porque para conseguir las producciones más altas. Entonces, si quieres hacer cosas a nivel industrial, puedes llegar a gramos por hora, producción de distintas nanopartículas. Con nano, por ejemplo, el tamaño también puedes cambiar. Y, por ejemplo, con la técnica que he enseñado de si tienes ya un coloide, reirradiar, con nano, por ejemplo, puedes reducir el tamaño, pero en determinadas... Eso es más complicado, pero si consigues encontrar la ventana de parámetros, de intensidad y demás, puedes incluso que crezcan, porque empiezas a fundir un poco la superficie y consigues que las distintas nanopartículas vayan uniéndose y creciendo en alguna más grande. Hay muchísimo juego.
Lo otro era, ¿cómo demonios dispersas son las distribuciones que obtienes?
No son, depende del láser y demás, pero ahí perdemos claramente con los métodos químicos. Solemos tener distribuciones de, creo que tenía la plata por aquí, es bastante, esto por ejemplo es bastante estándar. Pues una anchura a lo mejor de, bueno, de hecho aquí el PDI un poquito era 0,05. Pero esta es una distribución típica, por ejemplo con nanosegundos lo que sueles tener también a veces es una distribución bimodal. Tienes a lo mejor un pico con oro, por ejemplo, suelen salir sobre 20 nanómetros y otro pico más cerca de 40 nanómetros. Luego puedes centrifugar y separar o eso. Depende también mucho de los parámetros y demás.
¿Habéis pensado en hacer reshaping? Porque, o sea,
Bueno, he visto sus papers y que los tengo. Sí. Los nanorods. Sí. Sí. Es un poco... La idea era, bueno, era esta segunda técnica. Era un poco así. Lo que pasa es que, claro, lo suyo también era específico con los nanorods, muy controlados. O sea, ese paper es una pasada. En general es eso. También depende mucho de los materiales, parámetros. Tienes que mirarlo en cada uno, pero sí. Tienes mucha versatilidad, eso es lo bueno, para bien y para mal.
¿Una pregunta más?
Gracias.
Una pregunta simplemente. Has hablado sobre los scaffolds, ¿no? Para aplicación regeneración ósea, entiendo, que son antibacterianos. Pero ¿habéis estudiado la toxicidad de los scaffolds?
De momento no. Estos fueron los primeros. De hecho, estas medidas, por ejemplo, lo hicimos como a concentraciones muy bajas porque normalmente la idea es, o nuestra idea inicial, es usar muy poco nanomaterial, por un lado, para que sea más interesante porque incrementa el precio menos. Por otro lado, porque no tienes que cambiar los parámetros de impresión. Entonces, si tú vas a una empresa y les dices, vale, te cambio el material, pero tienes que cambiar todo tu, tu procedimiento. Entonces, es un problema. Si añadimos muy poquito, normalmente es cambiar un pelín los parámetros. Entonces, por ejemplo, lo digo porque la concentración es muy baja, es 0,1% en peso con el polímero, y el efecto bactericida no es directamente en contacto. Aquí, por ejemplo, solo lo vimos en inmersión, digamos, en inmersión en el medio de cultivo y después en ese medio. Pero, por ejemplo, con contacto directo hemos hecho test y ahí de momento no tenemos propiedades bactericidas. Si aumentamos concentraciones, yo creo que no habría problema.
Sí, pero en cualquier caso es fundamental estudiar la toxicidad porque si lo quieres aplicar para aplicaciones biomédicas, en cualquier revista pues te van a decir, pero bueno, ¿esto es tóxico o no?
Sí, estamos ahora en ello. Muchas gracias.
Gracias, Carlos.